Hello and welcome to the astrO podcast. Today we'll be exploring galaxy collisions and their interactions and the role of friction. How does friction come into all this? Well, there's a new term we'll be learning today called dynamical friction, which is basically which helps slow down objects which help galaxies merge together. We'll also be learning how studying these collisions can help us understand dark matter better and the amazing effects of black holes on galaxies. Also, another new term called black hole lensing, which it might sound familiar because there's a familiar term called gravitational lensing, which is basically um, when massive objects like galaxies bends light around it. This is quite similar to black hole lensing, and this bending of light kind of acts like a huge cosmic magnifying glass. Now, black hole lensing is basically the same thing, but with more dramatic effects because of the immense gravitational field of black holes. Will join us on this journey to the wonders of the universe. Hello and welcome to the astrO podcast. Today we have the honor of being joined with Uddipan Banik, who is a postdoctoral research scholar at the Department of Astrophysical Sciences at Princeton University and a member in astrophysics at the School of Natural Sciences in the Institute for Advanced Study at Princeton. His work involves galactic dynamics, dark matter, and plasma astrophysics, and how galaxies evolve over time and through their different processes. So thank you very much for joining us today, Dr. Banik. And so before we start, could you please give us a brief introduction of yourself, like what got you into astronomy, how did you enter Princeton, and so forth?
Yeah, well, it's very nice to be here. Thank you for having me and listening to me. So, I have always been interested in astrophysics in general. Since right from my childhood, I was always wondering about what lies up there. When I used to look up at the night sky, I was struck by wonder as to what is happening out there in the thousands and millions of stars that we can see every night. And um, it was mostly my grandparents who actually first inspired me to pursue astronomy. My grandmother was very much into it. She used to tell me stories and all. And then in school, I was very much inspired by my physics teacher and my mathematics teacher to read some good books on popular science mostly, and those were by Stephen Hawking. And later on, I also got to read the book by Brian Greene, and so especially the book by Stephen Hawking, which is called The Theory of Everything. It's very popular. It's one of the best sellers. So I read that when I was in the seventh or eighth standard, I think, and I didn't understand most of it, but at least I got the gist of it and I got the flavor, and that really struck me as to that one can actually understand or try to understand the basics of how the universe works with the help of concepts that you can also apply in everyday life. So physics is basically the answer to that. It is the answer to every possible question that you can have about the nature of existence and the nature of the universe. And that's what got me into trying to pursue this field. Then after leaving school, I went to IIT Kanpur to do BS Physics. And that's where I was introduced to the various concepts of different branches of physics. And after that, I applied for grad school to the US, and I went to Yale for doing my PhD in astronomy. Um, so I had a background in physics, but then I got introduced to the different concepts and topics in astronomy. So I ended up doing my PhD in theoretical astrophysics. And that's basically how I have entered this field. And now I am at Princeton, and it's one of the best places to do theory, which I really love to do. So I guess that's how I got into it.
That's really interesting to hear about your childhood, how you got inspired by astronomy and you're leading your way up into astronomy and then astrophysics. That was very interesting. So thank you for sharing that. So let's just head right into the questions. We'll be having three topics that we'll be exploring today on galaxies, dark matter, and black holes. So let's just get into the first question. So, what is a surprising phenomena that you have observed during observing galaxy collisions?
Right. So galaxy collisions, they happen all the time. You can actually see these things happening when you look up to the sky and look through the telescope. You can find many merging pairs of galaxies. And the farther uh, in the past you go, you can actually observe more and more of these merging galaxies. Now, the curious thing about the collisions between galaxies is that it is kind of different from the collisions that we normally tend to think about in everyday life. So because these collisions happen due to gravitational encounters between galaxies. And in our everyday life, whatever collisions we think of, those happen due to electromagnetic encounters. It's a very different force than gravity, although it behaves like gravity in a certain regime. But the gravitational encounters between galaxies happen on very large scales, and the galaxies can actually feel the gravity of one another from quite a large distance. And a surprising phenomenon that people have, well, there are two surprises actually, I should say, that people have wondered about in the context of galaxy collisions. One of them is that the galaxies tend to forget about their uh, past, or I should say, history, after the collision has taken place. So, after the collision happens, the galaxies rearrange themselves, which is known in technical terms as revirialization. It's a mouthful, but basically that means that there is a memory loss that happens. So, the galaxies tend to forget their history. The gravitational encounters between the stars, they shuffle around the initial conditions so that finally the galaxy looks very different from what it initially began. So you can actually do this thing in a computer simulation. You can take two disk galaxies and make them collide. And after the collision, all what you have is an elliptical galaxy, which looks very different from a disk galaxy. So this is one surprising phenomenon, and there is not a lot of good explanation about what is actually happening here. So that is one of my current topics of research. This is also known as violent relaxation because this happens very violently, that is on time scales that are way shorter than the typical dynamical time of the average dynamical time of the galaxy. So this happens quite fast, in other words. So that is one surprising feature. How do galaxies lose their initial conditions or knowledge of initial conditions of history? There is another curious feature that happens in galaxy collisions. One galaxy tugs at the other galaxy and pulls some of the stars from it. And that creates a sort of a tail of stars that recedes the galaxy. And this is known as a tidal tail or a tidal feature. You can actually see these tidal features when you look through the telescope, yeah, and you look at merging pairs of galaxies. Some of the features can be explained, but there are other features that you observe in galaxy collisions out there in the universe which you still cannot explain through computer simulations. So I guess that those are two surprising things that come to my mind when you talk about galaxy collisions.
Actually very amazed about how galaxies can have like forget their past. So that's a very interesting thing to look at. So also I was reading about like your papers and your series. So what is dynamical friction in galaxies? Like what exactly happens in that?
Yes. So dynamical friction is a very interesting concept, and as the name suggests, it has to do with dynamics and it has to do with friction.
Mhm.
So the reason why it's called friction is just the same reason why anything is called friction in everyday life. So, for example, when you rub your hands together, they get hot because you are actually using some of the kinetic energy of the motion of the hands, and you're putting it into the random thermal energy of all the electrons and atoms that are there in your hands. So there is, in a sense, a
Mm-hmm.
sort of transfer of energy from regular ordered motion to random disordered motion. And this process increases entropy in some sense, which is, well, it is a measure of the amount of order or disorder in a system. So the more the disorder, the more is the entropy. So this is how friction works. You are putting some regular energy into some irregular or disordered form of energy. And in galaxies, the same thing happens, but due to different reasons. So in everyday life, again, similar to what I was talking about in the context of galaxy collisions, in everyday life collisions or friction, they happen purely due to electromagnetic effects. But out there in the universe, this friction happens due to gravitational encounters. So just as one hand is encountering another
Mm-hmm.
hand and is transferring some energy via friction, similarly, a massive object out there
Yes.
in space, let's say that can be either a black hole or a globular cluster or
Okay.
any star cluster, something that is way more massive than any single star, that can actually interact with the surrounding stars as it is moving through a sea of stars in a galaxy. And this interaction is gravitational. Now, as the object is moving in space, it is encountering a lot of stars coming from the front because just of its motion. There will also be stars that are going to be pulled up from behind, but there are only always going to be an excess of stars that is coming from the front
Mm-hmm.
just because of the way you are moving. What that means eventually that you are going to lose energy. This body, this massive object is going to lose its kinetic energy and momentum to the particles with which it is interacting. And on an average, it loses energy. There can also be cases where it gains energy, but mostly it loses energy. That's why it's called friction, because it is losing its kinetic energy and giving it to the random energy of the stars that are moving around at also sort of random orbits all around itself. So that's the friction, and the dynamics comes from the fact that it is happening due to gravitational encounters. So anything that has to do with gravity is called dynamics because it changes the orbits of or orbits of the system or the orbit of this massive object in this case. So that's dynamical friction.
Mm-hmm.
That is how it operates in galaxies, that you have one satellite galaxy, for
Yes.
example, a small galaxy that is moving in a host galaxy in a much bigger galaxy. And that small galaxy is
Okay.
encountering or gravitationally interacting with the stars of the host galaxy and slowing down. And as it slows down, it actually inspirals, it loses its energy, and therefore its orbit becomes smaller and smaller until it goes to the center of the host galaxy. And this is how actually all large galaxies form. They form by making the smaller galaxies lose their energy and go all the way to the center of the galaxy. And that's how the galaxies grow in size and mass. And this is known as galactic cannibalism. This is how all large structures form out there in the universe, that smaller galaxies merge together to form bigger galaxies. And that's how dynamical friction works. And it can actually explain how galaxies form.
So it's crazy to think about how friction can also be observed in like huge objects like galaxies. And there's so many new terms that are like that I'm learning as well, like this
Mhm.
gravity cannibalism.
Yeah,
So
it's a very fancy term.
so why is it important to understand how friction stops in a galaxy, and how could this like enhance our knowledge about the universe, or like as you said, galaxy formation? So
Yes. So when we talk about dynamical friction, we usually tend to think that all galaxies will eventually lose their energy to the surrounding particles and therefore will go all the way to the center of the massive galaxy through which it is moving. But that always doesn't happen. That happens depending on whether the host galaxy through which it is moving has more stars or less stars towards the center of the galaxy. This process can be either more efficient or less efficient. So if the host galaxy has a lot of stars in the center, then its density profile is steep, or in other words, It's known in astronomical terms as a cuspy galaxy. It has cusp towards the center, so there is a lot of stars, a lot of matter towards the center. And when that happens, then dynamical friction is super efficient, and your satellite galaxy or this massive object is going to lose its energy continuously and go all the way to the center. But this story changes when there is not enough stars in the central part of the galaxy through which this massive object is moving. When that happens, then the host galaxy is known to have a core. It's known as a core density profile. Instead of a cusp, it is a core. Now, in a cored galaxy, dynamical friction can actually become very inefficient, or actually even go to zero, when the object loses its energy and reaches the core radius. So it does not want to go much further in, it stalls at a certain radius. And the reason that happens is it was not actually well understood why that happens before I came into the field and gave an explanation for that using theory. So the reason that happens can be understood as follows. See, the dynamical friction is happening due to gravitational encounters between these objects and all the surrounding stars. But in order for these interactions to actually change the orbit of this massive object significantly, you would like to have something known as a resonance. Now, a resonance is, you can sort of understand it in simple terms, that it happens whenever the frequency of something matches with the frequency of some other thing. Let's say that you are hitting a fork with a stick or with a spoon or something. Then when you hit it at the right frequency, you will hear a ringing sound. And that's how all tuning for experiments, for example, go, that if you hit it at the right frequency, then you are going to hear a large amplitude sound, a very loud sound. That's because your hitting frequency matches with the natural frequency of the molecules inside that object. And a similar thing happens here. When the massive object is it's moving around in an orbit, like a circular orbit, let's say, for simplicity, that has its own frequency. It's going round and round at a certain frequency. And the stars are also moving around at their own frequencies in the galaxy. Now, when the frequencies of the stars are commensurate or sort of nearly equal to the frequency of the motion of this massive object, that's when you have a resonance. And since there are more stars in the inner part than in the outer part, and therefore more stars with smaller energy, they're going to gain energy on an average from the object, and the object is going to lose energy in this process of resonant interactions. And that's how this object moves further in, by pulling stars out from the center. Now, these resonant interactions happen when there are a lot of stars that are moving around at frequencies that are comparable to the frequency of this massive object. But when the galaxy has a central core, then there is a mismatch between the frequencies of the stars and the frequency of this massive object. That's because in a cored galaxy, all the stars are moving around at nearly the same frequency. So there is not a very large frequency spread. In that case, this massive object can actually move at a frequency that is significantly different from the frequencies of the stars, and therefore there is no resonance, there is no frequency match, and that's why there cannot be a lot of energy exchange between the stars and this object, and so dynamical friction doesn't operate anymore, and therefore you have a natural stalling of this object at a certain radius because it just cannot talk to the other stars anymore. So that's how core stalling works. So this phenomenon is known as core stalling. It is the stalling of dynamical friction in core galaxies. Why this is important in understanding galaxy evolution is because a lot of galaxies out there, we believe, actually have cores instead of cusps. So they do not have a lot of stars or dark matter near the center of the galaxy. It has a core profile. And till like even 10 years ago, people used to believe that dynamical friction is very efficient, whether it be a cuspy or a cored galaxy. But we actually found in computer simulations, and that is not the case, and that came as a surprise. And then I, with one of my collaborators, we proved that this actually has a theoretical explanation. You can understand why dynamical friction doesn't operate in a cored galaxy. So when core stalling happens, it can actually halt this dynamical friction, so the massive object doesn't go to the center. So supermassive black holes cannot form anymore, because the standard theory for supermassive black hole formation is that you bring together a lot of these smaller black holes to the center of the galaxy due to dynamical friction, and you make them merge, and that's how you form a very massive black hole. And that's how all supermassive black holes at the centers of galaxies form. That was the conventional understanding of this process. But that doesn't work anymore, because your galaxy has a core, and therefore you have core stalling, and therefore your smaller black holes cannot go all the way to the center because dynamical friction halts. So how then do you form supermassive black holes? And the explanation is along a different, has to be along a different path. Now you cannot really say that black hole mergers are happening in these core systems. So that's where core stalling is very important in predicting how black holes and galaxies are going to evolve together. For example, that's one application of this.
Wow, so that's a lot of information about but why is it necessary for a galaxy to have a supermassive black hole in the middle? Like,
Well, it's not necessary, but you see, when you observe with your telescope, you can actually see a lot of radiation coming from the center of almost every galaxy in this universe. And that amount of radiation cannot be produced by simple stars.
yeah.
That has to come from something else. You can see jets actually coming from the centers of many galaxies, which suggests that a lot of energy is output somehow into the outer space by some central engine that is going on in the center of the galaxy. And the most natural explanation is to have a very massive object in the center that has a lot of gravity, and therefore it's pulling the stars at enormous speeds, and the stars and the gas and everything is going around at enormous speeds. And when that happens, then it heats up. Those material that are going around the central object are going to heat up and release a lot of radiation. This is known as accretion radiation. uh, Now, since you observe this radiation, there has to be something at the center that is driving this process. And then you go and observe with your telescope as to whether there is actually something at the center. And then you observe nothing. You do not observe any significantly bright source or anything like that at the center, apart from this radiation that is coming in the form of jets and so on. Then the most obvious explanation is that there is something invisible in there, which is driving the motion of all this stuff around itself, and therefore it has to be a black hole. If not a black hole, then some other exotic object, but nothing normal. So you find this at the center of almost every galaxy, and that's why we believe that supermassive black holes are there at the centers of galaxies.
Either. Well, but like how like with all this information that you guys have on galaxies, like what observational tools or what kind of advanced technology do you guys use to observe these? Because obviously we're not seeing galaxies merge like this. So
Mhm.
how did you come up with these theories that galaxies can have these type of interactions with each other?
Right, that's a very good question. So, as you said, as you correctly pointed out, we actually do not see these things happening right now, because they were happening in the past, but
Yeah.
since the timescales are very long, it usually takes a giga year or billion years to
Yeah.
happen. So you do not see it happening. But what you can see, though, is sort of multiple events happening. So you can see one stage of galaxy collisions, that's just one snapshot. Then you can see another pair of galaxies that are in another stage of galaxy evolution. So that's another snapshot. And then you keep taking these photos. So you keep taking snapshot after snapshot of many galaxies out there. Because if the universe had just one galaxy or one pair of galaxies, then we wouldn't be able to tell anything about what is happening. But thankfully, we have gazillion galaxies. We have 100 billion, 200 billion galaxies in our observable universe. So we have a lot of data. So with telescopes, and these can be either optical telescopes or ultraviolet telescopes or any other radio and so on, we can actually see these different galaxy pairs or different galaxies that are evolving over different time scales and going through different stages of their lives, so to say. And that's why we can actually say what is happening, what should happen to even a single galaxy. Because whether you are taking multiple images of different galaxies or you are taking multiple images of the same galaxy, it should be statistically the same. And that's the idea. It's called the ergodic hypothesis. And therefore, you can understand what might happen to our own galaxy or any other galaxy by looking at what is happening to many, many galaxies through different stages of their lives. Yeah.
I think we've been talking a lot about galaxies, so I think we should maybe move on to dark matter. Basically, a dark matter will also link with galaxies as well. But how, like I was reading that, how does your work on galactic dynamics help us understand dark matter better?
Right. So that is one of the key questions in modern astrophysics and cosmology as to what is the nature of dark matter.
Mm-hmm.
Galactic dynamics is one of the ways to study the nature of dark matter, or where there is dark matter, whether there is enough dark matter, and so on. And all those questions can be answered. Now, the way it works is as follows. So, in galactic dynamics, we look at the motion of stars. We see how fast the stars are moving, or any other visible object is moving, be it gas or stars or anything. We can tell by looking at the telescope, we can actually observe the Doppler shift of the frequencies of the radiation that is coming from the stars. So, if the star is moving towards us, then the light is going to be blue shifted. If it's going away from us, it's going to be red shifted. So we can actually tell from the light that we are receiving in our telescope from the stars whether it's moving away from us or towards us, and at what velocity it's moving. So we have the velocity information. This is known as radial velocity spectroscopy. And we can also tell at what velocity the star is moving on the plane of the sky, so transverse to the line of sight to us. And that has been done by this wonderful, amazing telescope called Gaia, which has provided us with a lot of information about how fast the stars are moving, where the stars are, at what distance, and so on. So it gives us the full 6D information, so 3D in space, in position, x, y, z, and 3D in velocity, vx, vy, vz. So it gives us a whole bunch of information about how fast the stars are moving. And then we can go and ask the question, is there enough matter in the galaxy to make the stars move at that velocity? And what we observe is that no, there is not enough matter. The self mass of all the stars put together in the galaxy is not enough to make the stars move at the velocity that we see. So then comes the question as to what is this extra force? Where is it coming from? And one of the candidates is dark matter. It can also solve many other puzzles in the universe. And it says that, there is this missing component of matter, which is very different from normal matter. And therefore, it does not interact with normal matter in normal ways. So it does not interact with light or with any kind of normal baryonic matter. So basically stuff that we are made up of, it's known as baryons. So it does not interact with normal matter, and that's why we can't see it. It's dark, but even though we can't see it, it has its mass, and if it has mass, then it has gravity, and therefore it can pull the stars through its gravitational attraction, and that's how it is making the stars move at these very large velocities. That was one of the explanations for these velocities of stars that we observe, that dark matter is the one that is doing it. Now, that was observed, or sort of that this theory was postulated around in the 1930s to begin with, and then it was followed up and confirmed by many other observations in 1970s and 80s. But that was all done with just one component of velocity, just the radial velocity. But now we have all three components of velocities. We have observed that for many, many stars, at least 1 million stars now with Gaia telescope. And so we have a lot of information. So we can definitely say much more about the nature of dark matter. If the dark matter is sufficiently cold, that is, if the dark matter particles are moving at very small velocities, let's say, so this is known as velocity dispersion or thermal velocity. It's like the temperature of dark matter. If the temperature of dark matter is very small, then it behaves in a way that is different from the way that it would have behaved if the temperature was large. So warm dark matter and cold dark matter behave in very different ways. Cold dark matter tends to form much stronger over densities of matter, so it tends to make the matter pile up because the temperature is much lower and the density is higher. And warm dark matter tends to sort of fuzz out the matter over densities because the random motion of the particles is going to kill any small scale inhomogeneities in the matter distribution. So these kinds of things happen when you change just the temperature parameter of dark matter. And now you can change the dark matter particle mass. So these are all theories, basically. Nothing has been observed so far. We do not know what dark matter is made up of, but we can actually tell from particle physics what kind of matter it can be, what can be its mass, what can be its interaction cross-section and so on, what can be its temperature and so on. So all of that we have theories for, and we can now go and test these theories against observations. So we can literally see in computer simulations how cold dark matter interacts gravitationally. Remember, gravitationally, there is no other kind of interaction that happens. Maybe some weak interaction, but only gravity that is important. How cold dark matter interacts gravitationally with the stars, we can model that in the computer simulation, and then we can compare that to observations. Similarly, we can model how warm dark matter interacts with the stars, and we can compare that to the observations. And this is how the topic goes. This is how the research is done in trying to understand the nature of dark matter by looking at how it affects the motions of stars.
Actually, it was like kind of the first time of me hearing what cold and hot dark matter was. So actually that was leading to my next question was, what do you mean by hot and cold dark matter? What's the difference? And also you'd mentioned, I think, what is when you say it's fuzzy as well.
Yes.
So, well, I would just like wanted to break it down, like what it means.
Yes. So cold and hot, you can understand that it's either cold or hot. So its temperature is small, it is cold, its temperature is large, it is hot. Fuzzy is different. So let me get back to fuzzy in a second. But let's first look into what I mean by cold. How cold is it actually? Now, cold dark matter is called cold because the dark matter particles are moving at very small velocities compared to the velocities of the stars in the surroundings in the central part of the galaxy. So there, actually, the dark matter is moving at very small velocities, but that doesn't mean that the dark matter particles are moving at small velocities everywhere. And so there is another interesting thing that happens. So in the early universe, everything was coupled to everything else. So the dark matter and the baryons, they were all strongly coupled in what is known as primordial plasma, or soup, you can say. And those kind of interactions, apart from gravity, there is some kind of other interaction that happened back there in the very early universe between dark matter and normal matter. That is not in the standard model of particle physics. That has to be something beyond which we do not yet understand. But once the dark matter particles sort of stop seeing the other matter particles, because the density of the universe is going down as the universe is expanding. And as that happens, then there are not enough interactions that are happening anymore between the normal and the dark matter particles, and also in between the dark matter particles. And that's when the dark matter sort of decouples from the primordial plasma. It decouples from the normal matter. And when that happens, you have to ask what is the temperature of the dark matter particles when that decoupling happens. And if that temperature is such that the dark matter particles are moving at speeds well below the speed of light, then you say that the dark matter is cold. But during the decoupling, if the temperature of the dark matter particles is comparable to the speed of light, not as large as the speed of light itself, and nothing can move faster than the speed of light, of course, but if those particles are moving at somewhat speeds that are somewhat similar to the speed of light, then we call that hot dark matter. And if it's in between, then it's warm. So depending on the temperature of the dark matter particles, when it decoupled from the primordial plasma, we classify them into cold, warm, and hot. So that's the explanation for why you call it cold or why you call it hot or warm. Now, why are there these different models that we came up with? We came up with these different models to explain structure formation in the universe. If the dark matter particles are very cold, then these particles sort of try to clump together, right? You can sort of try to understand that just physically from everyday experience that if something is cold, something is not moving very fast, then it is going to not be at the same place for a long period of time, and therefore
Mm-hmm.
these particles are going to see each other and going to see the normal matter particles as well gravitationally for a long period of time, and therefore it's going to make things clump together more. And that's why you get more and more galaxy formation or structure formation in the universe if you have cold dark matter. If you have warm dark matter or hot dark matter, then these particles are moving fast, and therefore they are not going to make matter clump at that rate, and therefore structure formation is going to be less in the universe. So we look through our telescope, we see our galaxies, and we try to understand how many galaxies there are and what part of the space and in what quantities, what is the density of these galaxies, and so on. And from that, we can try to understand what the nature of this dark matter distribution might be, whether it's cold or
Mm-hmm.
warm or hot. Now, fuzzy dark matter is a very different beast. It is, well, the name suggests
Yes.
fuzzy, so it means that there is something to do with uncertainty. And now we have to go all
Okay.
the way from classical mechanics to quantum mechanics. So in quantum mechanics, there is this uncertainty
Mm-hmm.
principle, which was, postulated by Werner Heisenberg. It's Heisenberg uncertainty principle. It tells you that you cannot measure the position and velocity of a single subatomic particle with infinite precision. If you measure its position with a very large precision, you have to measure its velocity with very small precision, and vice versa. So this means that if your particle is very light, if it has very small mass, then its uncertainty is going to increase. This is what happens for electrons, for example. You cannot measure the position or velocity of an electron simultaneously with infinite precision, although you can measure those things very well when it comes to a billiard ball, let's
Mm-hmm.
say. So any macroscopic object, you can tell at what velocity it is moving and at what point in
Yes.
space it is, but you cannot tell that precisely for a subatomic particle or a very light particle.
Okay. Yes.
Now, if dark matter is made up of very light particles, and these particles actually have mass much, much smaller than the mass of the electron, even. If I can give you an estimate, it is like 20 orders of magnitude below the mass of the electron. So these are super light particles. And why do we make it so light? So that its uncertainty in space becomes very, very large. It actually becomes astronomically large. So it is sort of like the particle is like a wave, and the wave is spread out over a huge region of space, and that's what makes it fuzzy. So it's fuzzy on scales that are astronomically large, around a kiloparsec or so. So 1 kiloparsec is 1,000 parsec, and 1 parsec is 3 light years, if that's how it goes. So it's spread out all over the galaxy, actually. Even one particle, the wave function of one particle spread out over a large region of space. And this fuzziness of the particle was introduced to explain again how much structure there is, how clumpy the galaxy is. If the galaxy is not very clumpy, then it can either be warm dark matter or hot dark matter or fuzzy dark matter. Now, warm and hot dark matter actually have their other problems. To explain away those problems, this fuzzy dark matter candidate was introduced. And the curious thing is that the fuzzy dark matter is made up of particles that are also predicted by string theory. So there is this theory of everything that people have been talking about for quite a long time. It has its own problems, but it also predicts these many other interesting things, and one of them is the fuzzy dark matter. And it comes from string theory, but it can also explain some of these observations about galaxies out there through this fuzziness or uncertainty in position that comes from its quantum aspects.
Well, I feel like that dark matter really is based upon what type of particle it's made out of, because we have so many theories, like you said, the Heisenberg affinity principle. And so I think at CERN or the LHC, they're already trying to find different candidates for the dark matter particle. But as soon as we understand what the dark matter is really made of, I feel like it can really enhance our knowledge more on dark matter, which would be very interesting.
Mm-hmm.
So, I think Now I really want to get into black holes as well because I'm also very interested on black holes. So was looking through your bio, of course, about me, and you also work on black hole lensing. So I think most of us already kind of know what gravitational lensing is, which was basically how massive objects bend light around it. So how does black hole lensing work?
Yes. So black hole lensing is similar in some respects to normal gravitational lensing around a star, but also very curiously different in some respects. That's because a black hole is fundamentally different from any other object.
Yeah.
It is something which is infinitely dense at the center, but it is also surrounded by a horizon. So nothing can escape from inside the horizon because the escape velocity at the horizon is the speed of light, and nothing moves beyond the speed of light. So if light cannot escape, nothing else can escape. And it's sort of this horizon that is covering or sort of hiding what is lying beyond, what is lying inside from our view. So we cannot know what is going on there. And the way light behaves around a black hole is somewhat different from the way light behaves around any other massive object. So when you go further and further out, if the light ray is coming with at a larger distance from the black hole, then it is going to bend in a similar way as to the way that it would bend in case of a massive star, because further away from the black hole actually looks like a star only, or like any other point mass. So it's going to be the same. But if you get closer and closer to the black hole, if a photon is moving much closer to the black hole, then it can actually get captured somehow in an orbit, in a trapped orbit, and it can go round and round and round the black hole, and then it can even take some angular momentum from the black hole. If the black hole is spinning, then it can actually gain some angular momentum, and it can actually gain some velocity, so to say, and speed up again, and then move in a different orbit. So it can go round and round and then move again in a straight orbit, uh, and leave. That's a curious phenomenon that happens for light when it is moving close to the black hole. It can actually get trapped into one of these orbits forever. It can keep going round and round. It can, of course, go get into the black hole, and then it's lost forever. It's not going to come out anymore if it is inside the event horizon. So all these interesting things happen. And the way these things manifest themselves in gravitational lensing is that now in normal gravitational lensing, when light is bending around a star, you see an Einstein ring. So it's called Einstein ring. It's a ring-like feature. So the if the light is coming from some distant source, which is behind the lens, which is the star, then the light is going to be sort of spread out into this ring, and it's going to be very much magnified because now all this light is coming from this very infinitesimally thin ring, and you can actually observe this ring for many galaxies out there or many stars out there. So it's the same thing if the lens is a massive galaxy or the lens is a massive star. Except for a star, the ring is going to be much smaller in size because it's much smaller in mass, but for a galaxy, the ring is going to be much larger in size. Now, this ring can actually split up into two images if there is some line, if the star is lying on a line that is different from the line of sight of the distant source. And these two images basically correspond to photons either coming above the lens or below the lens. But for a black hole, there can be other interesting phenomena that happen. Because of these photons that can get trapped into these orbits around the black hole, there can be a significant delay in the light that you receive finally at the telescope, because light is trapped in this orbit for a long time before it escapes. So that time delay, this is known as Shapiro time delay. You can actually observe this delay happening because light will be coming from all directions. So it's not only going to bend in one direction, it's going to bend from the other side as well. And so you can look at these multiple images that are formed. In a black hole, you can actually observe many other images. It's not only two images or a single ring, you can observe multiple images, which is very different from what happens in a star. And by telling by looking at what is the magnification ratio of these images, or the ratio of the brightness of these images, you can tell things such as what is the spin of the black hole. It depends on the spin of the black hole, how fast the black hole is spinning. The mass, of course, you can get from the sizes of these images, or the size of the Einstein ring, if you have an Einstein ring. And you can tell what distance the black hole is from you, and what distance the black hole is from some distant source from which the original light is coming. And so you can tell a whole lot of information. But from these multiple images, the most interesting thing that you can tell is the spin of the black hole. And that's very much different from what would happen in case of a star.
Actually, my basic knowledge was like when light enters a black hole, it would never come out. But then now listening to this, I didn't know that what actually happened inside of the photon would keep orbiting around and gain angular momentum, but it can unfortunately never get out, obviously. So,
Yes, but the photon is moving in an orbit outside the horizon. So if it somehow gets inside the horizon, it's never going to come out. It's just going to go
oh,
in.
yes, of course.
But yeah,
Yeah,
it's something that is moving outside.
yeah. So, coming to kind of the end of the podcast, my second last question would be, we had said that um, when you talked about how when we look at galaxies, usually they have supermassive black holes in them, and that we can figure that out from the radiation coming from them or the jets. So my question is, how do black holes influence the formation or the behavior of galaxies? Like, what other ways can it like affect its behavior or so forth?
Yes, that is a very interesting question, and that is actually something that many people are trying to answer at the moment. That there is this huge radiation that can come from all this matter that is swirling around the black hole and getting heated up, and this is known as accretion. That the black hole is actually accreting matter onto itself as well. So it's making the stuff go around it because there is angular momentum, but that the angular momentum can be lost due to various processes, and matter can actually go into the black hole. And once it goes in, it never comes out. But when it is before it is going in, it's also getting significantly heated up due to friction between the different layers of matter, and that releases a lot of radiation. Now, this radiation is very strong. It comes in a whole range of frequencies from the very close to the disk. So all the matter is actually going to pile up in nearly a disk around the black hole. Close to the disk, the radiation is very high frequency. It comes in X-rays and gamma rays. Farther out from the disk, it comes in infrared and smaller frequencies, because this high frequency radiation is going to be scattered off other particles and it's going to lower its frequency. So it goes to radio and infrared and to much lower frequencies. So you can observe all these different light that is coming from different parts of the disk. Now, and I should mention this structure, this disk that is forming around the black hole is known as an accretion disk. And this entire thing is actually known as an active galactic nucleus. So all this is happening in the nucleus, or the very central part of the galaxy. And since it's sending out a lot of radiation, it's called active. So it's called an active galactic nucleus, or AGN in short. Now, this radiation can definitely affect a lot of things that are going on in the rest of the galaxy. Since it's hot, this radiation it's got a high temperature. It's a lot of radiation that is usually in very large frequencies. This is going to stop star formation that is happening in the outer part of the galaxy. Now, stars form when gravitational collapse happens in the gas. It's going to collapse under its own gravity in a given region of space. And during the process of collapse, if it is able to cool as well, because as it collapses, it gets hotter and denser. And as it gets hotter, it's going to emit radiation. And in that process, it's going to cool and collapse further. So if it is able to cool, then it's going to keep on collapsing. And during collapse, it can actually fragment into smaller regions. And ultimately, those smaller regions are going to collapse further and form stars. when the nuclear burning temperature is reached, that's when nuclear fusion happens and it stops the collapse and it causes stars to form. That's how stars form in the gas in galaxies. But if there is this immense radiation that is coming from the active galactic nucleus around the black hole, that's going to interfere with this process. And all that radiation is going to heat up this gravitational collapse, this area of the galaxy where gravitational collapse is happening and stars were forming. But this radiation is going to interfere with that process and it's going to heat up this region of space. And that's going to halt star formation. So this is known as feedback. It's a fancy term. It just means that the radiation is going to halt the star formation, and so now there are less stars that are forming, and therefore less material that is going around the black hole, and therefore less radiation. So it's a self-limiting or a negative feedback that can happen. So it goes on in cycles. So that's how basically black holes and galaxies sort of co-evolve. If there is more matter going around the black hole, there will be more radiation, and this more radiation is going to halt the star formation, and therefore in turn there will be less matter going around the black hole, so it's going to stop this process after some time. So we believe that in many massive galaxies out there are these supermassive black holes at the centers of galaxies, which through this process of radiation due to accretion are going to halt star formation. And that's how you can actually get less stars forming in this galaxy than you would have if there was no supermassive black hole. So that's one way to explain this data, which plots the galaxy mass to halo mass or dark matter mass as a function of the galaxy mass. And you find actually that for a given dark matter mass, the galaxy mass is way smaller than what it should have been according to standard theories. And one way to explain that for the very massive galaxies is that there is some supermassive black hole that is sending out a lot of this immense intense radiation, which is going to halt star formation and therefore lower the galaxy mass. So that is one way that you can explain these things. And so that's how supermassive black holes can affect a lot of things that are going on in the galaxy.
Yes, it's very interesting to see that these black holes can really have an effect on gravity and galaxies, and that we can also observe them from far, and that we're using all these models and simulations to understand them. So actually, that was my last question, and no, my last question is actually not about these. It's basically on what advice or maybe some notes that you would give maybe young people who want to get into astronomy like me? Like how should they get into it? And mostly about that.
Yeah, of course, that is very important. I got some very good advice when I was a child, and there were very wise people all around me who were giving me advice, and some of that worked out. So one thing that has helped me is that you have to keep your curiosity alive at any cost. And if that doesn't happen, then at some point it feels like a burden, and then you lose your track. So it's very important to be motivated and curious and keep asking questions, and not only for astronomy, or not only for stuff that is very far from us that is going on in the universe. Of course, that's mind-boggling and that's very wondrous. But even for everything, everyday life phenomena, such as you look at the magnetic needle of a compass, and Einstein was very much surprised by why does the needle behave in such a weird way and point in only one direction wherever I go? And so this has to do with the magnetic field of the Earth that is going from South
Yeah.
Pole to North Pole and so on. So you can try to, you can be inquisitive about these things and try to explain or try to answer some of these questions. So it's very important to ask the question, but it's also even more important than that is to actually try and find ways to answer those questions. Now, that takes a lot of work, and but if you're motivated, then you will definitely find ways to answer that. And one thing to remember is that there are a lot of people that are also on the same level as you, or on different levels, that are also trying to understand things. So at some point well, I used to feel stupid at some point, and in my classes, or sometimes when the teacher used to uh, didn't explain stuff very well, or maybe it was my fault. But there are moments when you feel stupid, but it's not only you that is feeling that. There are other people who are also feeling that, and it's very important to just be aware of that fact and not be demotivated or
Yeah.
depressed because things are not working out in your favor. So yeah, I guess it's very important to keep up the curiosity alive and that little child alive inside of you, who is looking at awe at the night sky and trying to answer these very interesting questions. And some of these questions are very deep, and
Okay.
we have been able to answer a lot of these questions, but there are a lot of questions left to answer, and that's what life is all about. I believe that it's about trying to explain these unexplained phenomena and trying to answer these deep questions of the universe.
Yeah, of course. So actually listening to this, to your work and about galaxies actually made me more interested, and because I never really looked into like galaxies and their mergers and their formations, but this like really gave me a new perspective. So I'm really happy, and that's some amazing like advice to keep your curiosity up as well. So this is the end of our podcast, and of course, I hope we have the pleasure of you being joined with us again, maybe. But thank you very much for joining us today, and I hope you have a nice day as well.
Yeah, you too. Thank you very much. My pleasure. Thank you.